Alright, this is the homework key for the November 17th homework over chapter 11. Okay, first question wants to know how can we form this product where we have this primary chloride and the double bond has moved into the middle. So we know that we can't just make a carbocation, a primary carbocation to start off with, because one, it's going to be really unstable, and two, that might get our chloride on the end. That's not going to do anything about this double bond. So we need to start off like we normally do with these electrophilic additions, generating our more stable carbocation. Okay, so I'm going to put my carbocation here and put my H here, because that is the more stable situation. Okay, then remember, anytime we have a carbocation mechanism, we have to look out for hydride shifts that make even more stable carbocations, which is the case here because I can make this allyl or allylic stabilized carbocation if I do this hydride shift. Alright, so now I have a hydride here, and now I have my positive charge here. Okay, and again we said this is going to be resonance stabilized, so the other resonance form would be if I just move this double bond over one position. Right, and that's how I get my positive charge on the end. Right, this is where I would actually could see some addition to this end position, because despite being a primary carbocation, it's a resonance stabilization from a resonance stabilized carbocation. Okay. So in order to get this product that's shown in the problem, this must be the result of the chloride attacking that position. Okay, so this would give me my final product. You have to rotate it right from the way that I have it drawn, but right, we'd have chlorine 1, 2, 3, 4, 5 carbons. So chlorine 1, 2, 3, 4, 5 carbons, and then it's between carbons 2 and 3. 1, 2, 3, 1, 2, 3. Okay, on to next one. Okay, so another one of these where we need to think about what's the most stable carbocation that we can start with. So the most stable carbocation that we could start with is the allylic one, right? The resonance stabilized one. So let's go ahead and generate that. Okay, I want the allylic carbocation, so my positive charge is going to go here, which means my H went here. Right, and now I can see I get this resonance stabilization, which is why this carbocation is so favored. Right, these are my two main resonance forms I need to think about when I have a conjugated diene that I'm doing electrophilic addition to. Right, this one's going to be even more stable because, right, or I guess what I mean to say is we can continue, this particular carbocation is going to be even more stabilized by the fact that we can continue to draw resonance forms into this ring. But these are the only two resonance forms that give us products, right? The benzene ring stays intact because it's so stable. It's going to stay intact in final products. So either of these two resonance forms then can be attacked by my chlorine or my chloride nucleophile. So if I attack here, that's going to give me my first product. Alright, with my chlorine here and my double bond here. If I have a chloride attack this one, that gives me my other product. Right. Okay, now labeling these the 1, 2, and the 1, 4 addition products, remember the H goes on carbon 1. Okay, so this would be the 1, 4. And over here, carbon 1, 2, 3, 4. The H went on carbon 1 and the Cl went on carbon 2. So this would be my 1, 2 product. Right, remember 1, 2 is always the kinetic product. The 1, 4 may or may not be the thermodynamic product. You have to look at how substituted that double bond is. Right, your thermodynamic product is always your most stable alkene. Okay, on to number 45. Okay, so first part of this one, it wants us to draw all the possible carbocations that we could get for this particular reaction. All right, so I could put my H on this double bond, right? I wouldn't put it, sorry, I could put my H on the end here and put a carbocation in this position, right? I wouldn't want to put make a primary carbocation, but I could make a carbocation here. Right? I could, I guess if I'm drawing out all the possible forms that I could make here, then I suppose really we could consider at least making the primary carbocation. We can already kind of tell this not really one that we're going to consider because we know how unstable that is. Okay, so now I've looked at putting the carbocation in either of these positions of this alkene, and that's the same thing as looking at either of these positions on this alkene, right, since this is symmetrical. So now I just need to consider the two possible positions for the cation on this middle alkene. And again, because of the symmetry of this, they're actually equivalent whether I put the carbocation here or the carbocation here. So I need to just draw one that has a carbocation on this middle carbon. And I guess I'll go through and show where my H's went on these as well. Okay, so the most stable one of these, right? We know this one is going to be the least stable because it is a, or sorry, not this one. This one is going to be the least stable because it's a primary carbocation, right? We have it on the end. Then if we compare these two, this one has some resonance stabilization, right? I could move this over and put the carbocations delocalized between these two carbons. This one, I can move this, so I'll just go ahead and draw these out. This one actually has 3 resonance structures because I can move this double bond here. Put the positive charge on this carbon. Move this duct tape out of the way. I can put the positive charge on this carbon, and then I can move this other double bond over and do the same thing again. So I actually have 3 resonance structures that stabilize this one. Right, so this is going to be my most stable, and this is the one that everything is going to react from. These 3 resonance forms are the important resonance forms for this reaction of where my bromide is actually going to end up attacking. Okay. All right, so now the question asks us to draw the 3 products. So all of these products are going to result from bromide attacking these 3 different positions. So I could have my bromide attack here. I'm just going to show it as if it was the same bromide attacking all 3 instead of drawing this out 3 times. So I'll just say this, or this, or this, right? These are my 3 ways that my bromide could attack these 3 resonance forms of this carbocation, which is, again, the one that's going to react. So then my products would be just redrawing these and then attaching the bromine where that carbocation was. Okay, and then remember I put my H, so the next question wants to know what's the kinetic and thermodynamic products. That's what C and D is basically asking, right? It says which one is formed in the greatest amount of low temperature. That's the kinetic product, where we're limited by what forms the fastest. So kinetic is always the 1, 2. I need to figure out which of these was the 1, 2. So the hydrogen went on carbon 1, which is on this end. So this would be the 1, 2. This would be the 1, 2, 3, the 1, 4 product. And this would be 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. This would be the 1, 6 product. Okay, 1, 2 is going to be my kinetic. We said that's always your kinetic product because the nucleophile is right next to the carbocation as soon as this H goes on. Okay, so it's closer to almost being able to happen in one step. It doesn't happen in one step, but the 2 steps can happen very quickly, one after another. So this is my kinetic product. And again, this is the low temp. High temperature, I'm looking for my thermodynamic product, which is whichever one is the most stable. For alkenes, we're looking for the most substitution. So this one has 2 H's at the end, right? This one is disubstituted, disubstituted, disubstituted. So this is going to be the thermodynamic. Right, because these 2 both have terminal alkenes where there's just 2 H's here. Right, this one doesn't have any terminals, so they're both disubstituted. So this one's going to dominate at high temp. Okay, so we have this one that wants us to figure out several synthetic intermediates. So this first one is an acid catalyzed hydration. We just need to remember our OH is going to go, this is going to be Markovnikov, right, when we use just a regular acid. So Markovnikov means we need to end up with our nucleophile on the more substituted or more stable carbocation, which would be the benzyl carbocation in this case. And then from here, this would be racemic, right? Because we go through this carbocation intermediate. This OH would be, we'd have both enantiomers where this OH is a wash, where this OH is a dash, or where this OH could be a wedge. Okay, next one, we're going to use sodium hydride and this epoxide. We know sodium hydride is a base, and this is my most acidic proton. So I'm going to deprotonate this and then use this O like a nucleophile to attack my epoxide. Okay, and since I'm opening my epoxide in basic conditions, that means that I'm going to attack the less substituted side. Remember, acidic conditions, we attack the more substituted side. Basic, we attack the less substituted side. Okay, so if I want to draw what this would look like then, okay, here's my epoxide. And then since my epoxide is not shown with any stereochemistry, we're starting from this racemic epoxide. I'm just going to draw it this way. So I've just taken this and rotated it 180 degrees. And then I'm going to attack the less substituted side with my O, right, from this O right here. Okay. So now I need to connect this to everything else that O is connected to. So it's connected to a carbon, that's then connected to a benzene, and then this carbon fragment on the other side. Right, 2 more carbons. Right, so this would be an O minus after I open the epoxide, but then I add H plus to turn that back into an alcohol. Okay. So we might note we have, 2 stereocenters here to think about. Okay, then PBr3 is going to turn this OH into a bromide. Okay. And then finally, sodium hydroxide. So the first thing I looked at for this was, can I do some kind of intermolecular ring closing or intermolecular SN2 where something attacks this bromide? I don't have any acidic H's to pull off with my sodium hydroxide, except for the one that's adjacent to, on the carbon adjacent to the bromine, right? I could do an elimination reaction with this. Then I just need to consider, 1, how do I get this bromine anti to the hydrogen, and 2, am I going to make, how am I trying to say this? Where do I want to make my double bond? Do I want to deprotonate this carbon, or do I want to deprotonate this carbon? Okay, so we're going to deprotonate this carbon because that's going to give us the Zaitsev product, the more substituted alkene. Okay, so this is going to be my final product. All right, I'm going to deprotonate here, this bromine is going to leave, and that's going to give me my alkene product. Okay, so that's the end of this homework. I'll catch you on the next one.